Okay, time is 2:30, so let's begin here. So test number 2 is up here if you haven't already picked up your copy. The grades were largely okay. My comments regarding the exam were posted on the listserv. I don't really necessarily have anything else in particular to say about the exam. Did you guys have any questions? Okay, let's move on. Project number 5 is due on April 17th at noon. Are there any other possible questions before we get started?
Do we do all of it at this point?
Yeah.
Okay.
Yep. Test is there. Okay, so we left off last time on page 514. So the first part of chapter 5 looks at variable selection methods, where we have a situation where we have maybe a lot of variables, a lot of explanatory variables, and we don't know which ones to include in our model. And so we've looked at essentially 2 ways to make that determination, or at least initial determination. One was to essentially do what's called look at all possible subsets of variables, and from them look at the model that has the lowest information criteria. Now, when I say all possible, you got to be careful what that means. It doesn't necessarily mean all possible models that could be ever found. Instead, what it usually means is, let's say, all possible models that could be found where you just simply have all your explanatory variables as let's say, main effects or linear terms in the model, or equivalently, I should say equivalently, but alternatively, it could be, let's say, all main effects plus interactions. So at least gets you an initial idea of which models are potentially the best. And again, the lower the information criteria, the better the model. Now, a second method is to say, well, you could potentially have lots and lots and lots of terms to look at in your model. Is there maybe some kind of algorithm that could be used to search amongst all those possible models? And we looked at a particular algorithm called the genetic algorithm that allowed you to do that. It's not guaranteed to find the best possible model, but it's likely going to find one that's very good. And with that, we said, well, run it a few different times because of the stochastic nature of the algorithm to see if you get maybe potentially a better model in the end through additional running it. Now we're going to look at a third way to choose amongst, let's say, a best model. And that is what, and these algorithms within this way are called stepwise search algorithms. And what they try to do is, point that out. Okay, so again, the number of possible models that one could look at can be quite large. And the stepwise search algorithm tries to approach the problem like the genetic algorithm, where it tries to look at a large number of models to find the best one. But unfortunately, this method actually is not I'm going to use this word again, the best. If I had to order the 3 methods that we essentially have talked about, where you look at all possible subsets, genetic algorithm, and now the stepwise search algorithm, I would put them in that order. And typically, I wouldn't use the stepwise search algorithm unless I didn't really have necessarily any other alternative to do. Well, when wouldn't you have an alternative? Well, let's say you do have a very large number of explanatory variables, so you can't look at possibly all possible subsets. And perhaps maybe the genetic algorithm, for some reason, is not necessarily able to work. And you'll see a case of that in section 5.4.1 when we actually look at a case study, where for whatever reason, the genetic algorithm, the way that it was programmed into R with the function GM_multi, it just wasn't working right. And so if I'm left with a situation then where I can't do anything else, I can go ahead and use a stepwise search algorithm. So that gives you some justification for where we're going to look at it. Another justification for why we're going to look at it is that this is probably still the most prevalently used method out there. So, when you read other people's, let's say, research, you want to know, well, how does this algorithm work? Well, that's why we're going to talk about it here. So there's actually 3 different ways to do a stepwise search algorithm: forward, backwards, and alternating, you could say, where you alternate between a forward and a backward. We're going to focus on forward because once you know that, I think you'll be able to figure out the backward and the alternating. Okay, fortunately I didn't get my pen out. So again, you might be wondering, well, why do I say this is maybe the worst of the 3? It's because it's, let's say, you could say the least likely to find that best model. Okay, that's what I mean by it's the worst of the 3. So this is how forward selection works. First, compute the information criteria for a model with no explanatory variables at all. So if I were to use a GLM function and use the formula argument, let's say my response is y, what would I put after the tilde if I wanted to estimate this model? Excuse me? 1, exactly. So that's how you would estimate that model. The next step then is to compute the information criteria for all possible 1 explanatory variable models. What that means is, let's say you have 5 explanatory variables. Well, estimate a model with just, let's say, x1 in it. Then estimate a model that just has x2 in it. Then and keep on going until you estimate the model with just x5 in it. Compute the information criteria for all 5 models. The best of those models then is the one with the smallest information criteria. And if one of those models, if this best model has an information criteria that's lower than the model that you estimated in A, then that says that you have now a better model. So what forward selection says, okay, our new best model is this model that we just got in B. If, though, you have, of all these, let's say, 5 models, the model with the lowest information criteria is still larger than the model that you had in part A, then you would say, I'm going to stop the algorithm and just use the model that I had in part A, because based upon the definition of information criteria, the model with the lowest value is the best. So, but let's say that we found one model, maybe it just had x1 in it, just to make it simple. And it had a lower information criteria than what we had in A. And so then we go down to step C, which says now estimate all 2 variable models that have x1 in it. So you would estimate the model with x1 and x2, estimate the model with x1 and x3, x1 and x4, and x1 and x5. So you have 4 possible models that you would look at. And again, you get that information criteria from those 4 models. If one of those 4 models has an information criteria lower than the model that you get in part B, hey, you have found a better model. Use the model that has the lowest information criteria. And then move on to step D, where you essentially now look at all 3 variable models. That includes the 2 variables that you got from part B. And you keep on going to a point where you can't add any more variables because the information criteria is not decreasing, or you've exhausted all the variables. All the variables are in the model. That's forward selection. Are there any questions about that?
They consider interaction.
You could also consider interactions with that. Exactly. I chose to describe it in a more simpler setting where you just had the main effects. But yeah, you could include interactions. When you would do that, you would want to make sure that you include the main effects. So you couldn't look at an x1 and x2 interaction until x1 and x2 were in the model. And again, you keep on adding 1 term at a time. So let's say we had a situation where you had x1 and x2 in your model. Okay. Now you would look at x1, x2, x3, x1, x2, x4, x1, x2, x5, and the x1, x2, and x1 times x2. Those would be the terms if you chose to also include interactions. Any other questions? So it's not really too difficult to do. How about backward selection? Backward selection, if we look at the case again where we have 5 explanatory variables, we'll start with a model with, let's say, all 5 of those explanatory variables in the model. Then what do you think you would do next? Excuse me? Look to see if you can remove. So now look at them at all the models that have only 4 explanatory variables in it. If any model has information criteria lower than what you obtain with 5 explanatory variables, that says you have a better model. So choose that 4-variable model that has the lowest information criteria, and then go on to the next step. Look to see if you can remove some more. Then lastly, alternating stepwise selection alternates between forward and backward. So you perform a forward step, then you look to see if you can remove anything. Do another forward step, look to see if you can remove anything, and so on. Well, why might that be of interest? Well, let's say you get to a point where x1, x2, and x3 are in the model. And let's say maybe they were added to the model in that ordering. What can happen is after you add that x3 variable, now perhaps you could do a backward step. And then perhaps now, if you remove x2, the information criteria value could actually be lower. And so that's why it's sometimes nice to include both forward and backward. And then it has to do with the relationships between the variables. That's why that could happen. Okay, so let's take a look at an example of actually implementing this with the place-kicking data set once again. So there's a nice function R that essentially automatically does this for us. It's called the step function. And so first I'm going to read in my data. And then to do the step function, I'm going to estimate 2 models. The model that has no variables in it. So notice how I have a 1 there in my formula argument. And then also a model that has all the variables in it available in my data set. So if you remember from the last time we had a regular class, if I put a period there after the tilde, that tells R, okay, take all the other variables that remain in your data frame and put them as main effects terms in your model. So just a little bit of a shortcut syntax. Then, with the step function, I'm going to put the results into for.cell for forward selection. And for my object, I put in the smaller model. For my scope argument, I give a list where I specify the uppermost model that I would consider is what I just estimated with all the variables. And then I say direction equal forward. And then with that information criteria, I need to specify k. If I'm going to use, let's say if I use BIC here, if you remember the k is log of n. So I do log of the number of rows in place kick. Trace equal true tells me what happens at each step of this forward selection process. So we start off with a model that has no variables in it. So you're just estimating beta 0. Now note what R says. It says AIC is equal to 1020.69. No matter what you use for K, it will call it AIC. So we are actually using BIC, but the letters AIC will actually be printed. So please be aware of that. And so that's my BIC for the model that has no variables in it. And so it estimates all the 1-variable models. And notice distance, PAT, and change all lower BIC. But a lap 30 through field actually increase BIC if you were to include those variables in the model. So the model that lowers the BIC the most is the one that includes distance. So let's add distance to my model. So I do that. Now my BIC is 790.27. Now I look at all possible models that could occur with distance in the model and one other explanatory variable. When I do that, when I add PAT, my BIC does go down, but notice that for no other variable will BIC decrease. So I add now PAT to my model. I get a BIC of 784.2, and I do a third step where I look at, well, let's see if I can add another variable to this model that has distance and PAT in it already. And notice no model, no variable lowers my BIC. So then I stop. To get kind of a summary of the whole process, we can actually use the ANOVA function. And so we can see the ordering of terms that were added to the model. Okay, well, what happens if I were to use actually AIC itself? Well, what would you expect to happen? Would you expect to have more variables in the model in the end or less variables? Without looking at my notes. Well, what do we talk about for some of the differences between AIC and BIC in terms of what the end result gives you? One will tend to give you a larger model. One will tend to give you a smaller model. Do you remember which one was which?
BIC smaller?
BIC smaller, exactly. So let's see if AIC truly gives us a larger model. So, I mean, you can go through the details on your own here. So the AIC with no variables in it is 1015.43. Notice how distance has the smallest, results in the smallest AIC, so it's added first. Then PAT is added next. And AIC doesn't stop with that. It actually adds change to the model. And it actually adds when before it gets to a point where it can't add any more variables. Notice too, so with distance in PAT, the AIC is 768.41. When I add change, I get AIC lowered by a little bit less than 1. When I add wind, again, I have AIC lowered a little bit less than 1. So with change in wind and PAT, the AICs are not really too different. But still, again, this criteria says the lower the information criteria value, the better the model. I wanted to point that out, that they're kind of close, and we'll talk about that a little bit later, what that could mean for us. Okay, so let me move ahead here. So some comments: investigate backward and alternating on your own. I have it set up in my program so that you can do it. The corrected AIC, remember AIC with a little subscript C, you should expect that to give similar results to AIC. Does anyone remember why?
Large sample?
Yeah, because I have a large sample, and if you look at the correction itself, the larger your sample is, the closer the corrected AIC is to the regular old AIC. So whenever I have a large sample size, I would run the corrected AIC typically. Now you could do some of these things by hand, and what I mean by hand is actually program in to R, estimate each of these models, and then use the AIC function to calculate BIC or AIC. You could do it that way too. And as I said here, interactions could be included too. Okay, so that was the third variable selection way to go about doing this kind of stuff. Now, in my book, I talk about two other ones. And they're labeled in this section by modern approaches. Not necessarily saying that at least the first two approaches there's anything wrong with them. It's just the word modern means that they've come out more recently. So this one in particular, the LASSO, there's been a lot of research on that very, very recently. And we're not going to have time to talk about the LASSO, but I do just want to mention it. So it's one of the few cool names in statistics. So sometimes I wonder, some people, when they have an opportunity to name something, do they try to get the acronym just right so that, hey, I developed the LASSO. So anyway, so Tim Sharani developed the LASSO. He's a big name in statistics. And stands for Least Absolute Shrinkage and Selection Operator. I'm sure all of you knew that beforehand. And here's the basic idea. And it's a little bit like something that we kind of saw earlier in Chapter 2 when we talked about Firth's penalty for estimating a model when you have complete separation, if you remember that. And we really briefly talked about it. So with the log likelihood function, instead of just using the log likelihood function itself, add to it a little bit of a penalty. And what that penalty is going to try to do is it allows that, let's say variables that are truly not important, is going to force those corresponding parameters to be basically really, really close to 0. And also allows other variables to be more, just the important variables still to be shown as being important. And so you can estimate your let's say logis regression model or some other model using this LASSO, and then use this for a variety of models to see, well, which variables are important, which are not. The model with the smallest residual deviance is the one that's most important, yes?
What's the difference between the LASSO and the Stepwise when you have those forward and backwards at the same time and you get rid of non-important?
Well, before we did the LASSO, we were using the regular old likelihood function that we saw back in Chapter 2. What the LASSO does, it adds a penalty to the likelihood function, and you're trying to maximize that. That's the difference. Okay? The whole ultimate goal is still figure out which variables to include in a model. Now, the second one of these modern methods, which we will talk about, is called model averaging. I think this is kind of a really cool idea. I remember the first time I ever heard about it, it was probably about 10, 12 years ago. Actually, I won't tell you who, but a faculty member in our department was giving a presentation on it. And I was like, what? Why are you doing that? That doesn't make sense. So I'm purposely not telling what faculty member, because I don't want you to go to that faculty member and tell them that story. But since then, I have changed my thinking. And it's like, yeah, that makes a lot of sense, in fact. And so there could be situations where your information criteria for multiple models can be very similar to one another. Remember about five minutes ago, we kind of had something like that with the place-kicking data set. And while, yes, the information criteria that is the lowest corresponds to the best model, but if you have more than one model that has information criteria that are very similar, we'll talk about what we mean by similar later, you might be thinking, well, geez, that model is really it's almost as good as the other model. Can I maybe take advantage of that somehow? And that's what model averaging does. It allows you not to necessarily specify using one model, but you can use more than one model, and then essentially average the parameter estimates from those multiple models. And that becomes then your overall model that you use. Okay? Well, why does one want to consider doing something like this? Well, let's go back. So when I was using the BIC, if you remember, it found distance and PAT as the two variables to include in your model. When you do that, you're basically assuming then that you have a model that has 0 times change plus 0 times wind as your model, where the beta parameters are 0. Well, perhaps, maybe it's just due to your sample size itself, that you're just not able to find maybe a small wind effect or a small change effect due to your sample size. And so by just throwing them out, you're missing potentially very important information. And so that's one reason to consider this model averaging approach, because now what we could do is actually also include a model that has change in it, include a model that has wind in it, maybe both variables, and essentially for all those models, average over the beta hats, and then use that average value as your regular old beta hat that we've kind of used before. Okay, so this idea is model averaging. And we're going to use one, and this is still a fairly new area here. And we're going to look at one particular model averaging technique called Bayesian model averaging. And what it does, it calculates what you can say is a probability that a particular model is correct to use. And using these probabilities then, we're actually going to get a weighted average of our beta hats, rather than just normally what you would think of as a straight average. So that kind of makes sense to do that. If you have a model that has a very high probability of being correct, you want that corresponding beta hats to have a lot bigger of a role in deciding what the overall beta hat should be than a model that maybe has a low probability of being correct. And that's what this process does. These probabilities are estimated with the help of the BIC. So it's going to be a function of BIC. So to see what these probabilities are, let's define BIC sub 0 as the smallest BIC obtained from all subsets regression. So maybe, again, you look at all first order terms possible, look at all possible combinations of them, and look at all those possible models, calculate the BIC for each of them, find the model that has the smallest BIC. And let's define BIC sub m, little m, as the BIC for the model of interest. Out of, let's say we have a capital M models, just to be very general. Then the difference between these two BICs we're going to define as delta sub m. So it shows you how far you're off. How far is model M off from what we would have normally said is the best model. Then the estimated probability that the model is correct, the estimated probability that the model is the correct model, in terms of model M is the correct model, is approximated by this. So the actual estimated probability, let's call it tau hat sub m. And it can be approximated by taking e raised to the negative 0.5 times that delta, divided by the sum of all your e raised to the negative 0.5 deltas. So you can calculate, again, the delta for every single model. That's your estimated probability that a particular model is correct. The higher this probability, of course, the better that model is. And just because it's easier notationally, we're going to treat this approximate that you see up here as an equal. So, comments. First of all, we'll start with a question. What is the numerator for the model with the smallest BIC? What would that numerator be? So how do we find the BIC? I'm sorry, how do we find delta? This is too easy of a question. Okay, so delta is 0. So the numerator is? Not 0. What's e to the 0? 1, thank you. So that numerator will be 1 there. And you should think about, well, what will be all the other values? Well, less than 1, right? Okay. And you can see that if there is, let's look at, let's say, model, the model with the next smallest bit. Let's say that there's a big difference. Let's say delta's big here. Well, then what's going to happen to this? Well, that probability is going to be high for model 0, and for all the other models it's going to be kind of low. So if there's a clear-cut winner, then you're going to see that, again, we have that one model have a high probability, and all the other models have a low probability. So what happens to the probability as BIC sub m increases? Of course, then the probability is going to go down. Now, when delta is equal to 2, the numerator then ends up being about 0.37. And now notice that all these probabilities are based upon the same denominator. So that's why I'm just looking at the numerator there. And so that basically says that the model with if there is a model with a delta of 2, then this model is about 1/3 has a probability is about 1/3 of the model with the best or the highest probability. And people typically often use this as kind of a cutoff of judging, well, which are are often good models, and which are, that model is probably not worthwhile to look at. And one reason why I point that out is if we go back in the notes and look at some output that we got from GL Multi. Let's see here. You will always see something like this. 2 IC units. 2 information criteria units. That's talking about that delta. And so what it's telling you is, well, how many models are there that are kind of close to the best model? So that's why you see that there. Oops, went too far. Let's see. So 2 units of the smallest information criteria. Let's see now. All these derivations, obviously I'm not presenting derivations here, but all the derivations are done with respect to the BIC. And you do get what's called a posterior probability from doing that. So it is an actual probability. But you can use like the AIC in place of the BIC. You can use the corrected AIC in place of the BIC, but now it's no longer exactly a probability. And because of that, then these taus hats that we were talking about, people don't call them probabilities anymore. They typically call them as evidence weights. So the higher this tau hat, using one of these alternative information criteria, the more evidence there is towards using a particular model. And these tau hats you're going to see are essentially going to be weights when we find these averages of our beta hats. And again, unfortunately, I closed it out, but I'll give you a page reference. I can hold off on that. Never mind. Okay. So, what is a model, a Bayesian what is a BMA estimate? Well, let's say that theta is our parameter of interest. This could be like a regression parameter, like a beta, like beta 1. But just to be general, I'm just going to call it theta. Then theta hat sub MA for model averaged, then is just simply the sum over all your models of tau hat, that evidence weight, or that probability, times the corresponding parameter estimate from that model. That's it. So it's a weighted average. Now, what happens if you estimate? Let's say that we're working with regression parameters here. So let's say theta actually represents the beta corresponding to wind in our place-kicking data set. Now, we saw some particular cases where, excuse me, where maybe wind might not be in the model. Well, how would you find this estimate then if wind wasn't in one of those models? Well, you just simply take that corresponding theta to be 0. Because remember, that's what you're assuming. If wind is not in the model, hey, that beta is 0. So for models that you don't have that parameter in it, you just put a 0 in there for that theta. So some questions. Suppose one model has a smaller BIC, clearly has a smaller BIC than all the others. What do you think is going to happen is theta hat sub MA? It's primarily going to be based upon this one model that's clearly better than the others, because all those other tau hats are going to be quite small. Now, there's going to be one large tau hat for that really good model, and all the other tau hats are going to be small. So suppose many models, though, have a BIC close to the smallest BIC. What's going to happen to theta hat MA? Well, then all these other models are going to be really contributing to what that theta hat MA is, because all the tau hats are going to be kind of similar to one another, or a lot of tau hats will be similar to one another. So then lastly, well, for the last bullet, what would be the potential advantage to using BMA over other variable selection methods? Well, let me ask you, what do you think?
Well, it really just takes into account all of the models. Really, I mean, if you want some information about, if you want to use the information for some other model, it will be used a little bit.
Yeah, you're not going to be throwing away anything here. If wind might be helpful, well, hey, it's still going to play a role here. You don't have to make that decision, wind or no wind. I don't have to make that decision. I can let it play a role here. So that is an advantage. You don't necessarily have to pick, let's say, one model. You can have multiple models that all combine together to allow you to, find estimates, to do inferences and stuff. So just to make sure that you understand this, let's say theta was the regression parameter itself, as I was kind of leading to. That's what then the model average beta hat would look like. Well, what about a variance, though? We talked about how to get the estimate, but the estimate itself for a parameter. But what about the corresponding variance of that estimator? Well, this is the actual expression that one can use. The estimated variance of theta hat sub MA is equal to the sum again over all models, and look at that evidence weight, or that probability, its role. Again, if it's large, you're going to see that it's going to play a large role for a particular model. If it's small, it's going to play a small role. And then what we have here is the usual old estimated variance for that parameter estimate. And then we take theta hat M minus theta hat sub MA, so that overall estimate that you found above, and we square it. Okay. So for those of you who are stat majors, within those square brackets, what does that kind of look like? You would see something like this in Stat 883. Think of 3 letters. The first letter is M. Not that M. But thank you for offering a guess. The second letter is S. MSE, yeah. Remember what MSE is. The variance plus the bias squared. Okay, you see the variance in there. And that squared term kind of looks like a bias, doesn't it? Kind of. And so that gives you some intuitive understanding of where this expression comes from. And I say here, answer the questions above again, but now with respect to the estimated variance. So the questions above are the ones that are on page 523, those 3 questions. So just think about those on your own. The answers are essentially the same as what I had done previously, which is theta hat MA. So some comments. So BMA results in non-zero estimates of regression parameters corresponding to all explanatory variables of interest. Because you're not necessarily throwing anything out. Of course, if you have a variable that's truly not important, what's going to be theta hat MA? It's going to be something close to 0. Now, explanatory variables that are truly important are likely to appear in the high probability models. That's why they're important. Thus, their corresponding model average estimates will actually be a little bit closer to 0 than probably what you would have had. And doesn't happen in every case. Probably will be a little bit closer to 0 than what you would have had if you would just pick one model overall. And the reason why that happens is through model selection and just choosing one particular model, what often happens is that you end up making a judgment that a particular variable is actually more important than what it truly is. Meaning your beta hat will be farther from 0 than what beta truly is. And by using these models here where sometimes a particular variable might be in the model, sometimes it might not. What you have is a kind of a shrinkage effect, that these beta hats become a little bit closer to 0. And so it can potentially be very helpful then in terms of it will tell you, allow you to be more conservative. Well, I shouldn't say necessarily conservative. It will allow you to not necessarily include, what's the right word? It won't allow you to, let's say, it's likely make a mistake in terms of saying that one particular variable has a larger effect than what it maybe truly has. So that can be an advantage of using this approach. There are some packages in R that allow you to do this kind of stuff. In particular, the BMA and GL multi package. We're going to talk about the GL multi package here since we've already started talking about it before. Now, I have to admit that the availability of doing this kind of stuff in R and all other software packages, at least that I know of, is still not at the level that I would like, where anybody can simply apply it, similar to like the step function that we just saw. And so because of that, while we are going to talk about some with respect to what would be theta hat MA is, what the corresponding variance is, what we will actually end up using model averaging more so for is choosing one model to use. Because what comes out of this is, again, that tau hat. And that tau hat helps us essentially judge the correctness of a particular model. Okay, so let's take a look at an example here, again with the place-kicking data set. So I'm going to, similar to how I've used the GL multi before with the place-kicking data set, I'm going to say y is equal to good tilde and then a dot for all the variables. Level equal 1 basically again means that we are just using the main effects. H means exhaustive. The criteria I'm going to use is the BIC. And let's take a look what happens. I'm not going to show you all the output there because you do get a considerable amount. And instead, what I'm going to do is print off the results that we get from GL multi in terms of what's saved for us, or the default printing. And so what we see here, for example, information criteria uses BIC, level equal 1. The best information criteria, meaning the smallest, ends up being 784.19. This corresponds to the model that has distance and PAT in it, as we've seen before. Notice the word evidence weight. While these are actually posterior probabilities, this function just simply always calls it evidence weight. So this is our tau hat for the best model. One model within 2 information criteria units, meaning that by far this is the best model. Nothing's coming close to it. And if you wanted to look at all the possible models it takes to get up to a 95% evidence weight, meaning all the tau hats add up to at least 0.95, it takes 9 models to do that. Okay. So if you use the function weightable with the results saved from GL multi, you get information about the models and their corresponding tau hats. And so the best model, if I just use the head function with it, again, distance and PAT, here's the BIC. It has tau hat of 0.656, so quite high. The next highest includes change with distance and PAT, and it has a tau hat of 0.08. So overall here, do you think model averaging is going to produce much different results than what we would have had previously if we would have just chosen only the distance and PAT model? The answer is probably too obvious, so I'm going to say no, because all the other probabilities are quite small. So again, think about what's going to happen to your theta hat MAs. You're going to have one that had one of the models in that linear combination is going to have a very large weight to it, and all the other ones are going to have quite small. You can also use the plot function with the results from GL multi, and you can just simply see a plot of where all the models are essentially lying. This line is, I believe, drawn at where you would have at least 95%. Well, hold on. Yeah, where you have at least 95% of the evidence weights. Okay. Yep, that's why I have that. Good. So let's look at what then what our beta hats would be in this model averaging setting. So what I can do is use the co function for coefficients to basically pull off all the beta hats from all the models that were investigated. I put them in an object called parms, for lack of a better name, and I just simply do some reformatting to make some stuff look nice, and then do some rounding. And this is the table that's produced. So for the variable field, we can see to 3 decimal places, my beta hat MA is equal to 0. Of the top 100 models, it appeared in 29 of them. If you were to add up all the tau hats amongst these 29 models, they would sum to 0.026. And so what this does, it gives you some information then too about, well, is this a good variable to have in my model or not? Well, the probability is kind of small, so it's not. The 95% confidence interval, that you see, or CI plus minus there, what that represents is, and this is what the co-function gives you, is basically if you were to take, a regular old walled interval, theta hat plus or minus 1.96 times the square root of the estimated variance of theta hat, and what we learned back in chapter 1. Well, this part here is that. So I have an easy way to form a 95% confidence interval for the true beta corresponding to field. Let's look at some of the other terms here. So for example, for distance, beta hat MA is negative 0.088. It has an estimated variance of about 0. It's just like round to 3 decimal places. There is actually, it's actually non-zero. You have to take into account that we were looking with 0.088 there. Maybe I shouldn't have done that. Rounded to 3 decimal places. Notice it appears in all 100 models. And if you add up all the tau hats for the models where this appears, you get 1. To find a walled confidence interval, walled-like confidence interval that is, we'll take negative 0.088 plus and minus 0.024. You can see for PAT, it appears in 62 of the top models. If you add up all the tau hats, 0.944. So there's strong evidence that PAT should be included in any kind of model. But there's a lot weaker evidence than for some of the other variables. Down below then this table, then I actually show you the confidence intervals, the walled confidence intervals. And also I do this similar thing with the odds ratios too. Notice, for example, for field, estimated odds ratio is 1. Confidence interval is 0.99 to 1.01. Are there any questions? Okay, so some comments here. Let's see. So we can make some comparisons to, well, what happens if we just estimated one model with distance and PAT in it? And you can see this on your own. As we would expect, the beta hats are about the same with using model averaging or not using model averaging, again, because this particular model has such a high probability. And now, by default, and I failed to mention this, sorry, to find those intervals that we just did, those are actually t-based intervals. I'm not going to get into details why, but it uses a t-distribution instead of a standard normal distribution in doing that plus or minus value. If you want just a regular old normal based, you can use the argument IC method equals standard. Now you can also compute model average estimates for other stuff that we might be interested in, such as your pi hats, your estimated probability of success at a particular distance, and other combination. And I show in my program how to do that. Okay. So some last comments here. So these tau hats then can be used simply as a variable selection tool. And I've been alluding to that. So while we've been using them in terms of Bayesian model averaging, you can actually use them as a variable selection tool. So the model that has, let's say, the largest tau hat, then it will be the model that you would want to go with. Or if you see many models with multiple similar in size tau hats in terms of being the largest, then I might say, okay, maybe a model averaging approach might be better. Okay, we already did that. So in terms of these probabilities that we have, or the sum of these probabilities in this particular column here, there are some guidelines, kind of rough guidelines that Rafferty in 1995 gave about, well, what's a large probability in terms of, yeah, that variable is important or not. And on page 529, I just reproduced some of the stuff that he said for whether or not there's a lot of evidence or not a lot of evidence that a particular variable should be included. Okay, are there any questions? Well, let's move on to page 530 then. Tools to assess a model fit. So now what we've done is, through these variable selection through the variable selection process, we've come up with some. We've come up probably with like at least one model that looks good to examine further. In other words, determine, well, maybe we need some kind of transformation, maybe a square term for a particular variable in the model. Or maybe this model doesn't fit a particular observation well, meaning it has maybe a large outlier. Or maybe a particular observation is being very influential to what the model ends up concluding. And so what we're going to do is look at tools or diagnostic measures to help make these kinds of determinations. A lot of the stuff that I am going to talk about here corresponds directly to what will be done in a normal linear regression setting. In fact, these methods were often developed as simply extensions to what you would do if, let's say, y had a normal distribution to it. If you've had a full course on regression analysis, you've talked about these methods. If you haven't, that's okay. But if you would like to see it in the context of just a normal linear regression model, please take a look at my lecture notes from Stat 870. Now, before we get into these measures or these tools, I would like to make a few comments, a few other comments. I think overall this section was one of the most difficult for myself and my co-author to write. Going into writing this book, what we had hoped to do was for the models in chapter 2, 3, and 4, where for all of them, we would like to come up with tools to assess how well the models fit. And often these tools are very similar. We like to be able to talk about all these tools for all those chapter models all at once. What we found out early on is that that's difficult to do. And that's why probably most people don't do that. Very early on, we had to say, okay, we can't do this stuff with chapter 3, those multi-category models, because those are not actually generalized linear models. Unlike chapter 2 and chapter 4, those are generalized linear models, so they fit in the same family. So what we're going to do is focus on the models from chapters 2 and 4 here right now, and I'll talk about what you could do about chapter 3 models a little bit later. Unfortunately, the chapter 3 stuff, the tools are not actually as well developed as would be nice. So even though, okay, we were going to focus on chapters 2 and 4, we also found out, okay, there are little things that you need to worry about in chapter 2 models versus little things you need to worry about in chapter 4 models. So we had to go back and forth, well, what do we do? And so hopefully this discussion here, we'll try to put all this together and we will do side discussions about particular situations. And also we had to develop one overall set of notation that we could use too. Hopefully that will not be confusing. Now, one of these first side discussions is something dealing with chapter 2 models. To understand how well a binary regression model fits the data, so logistic regression, probit model, complementary log-log model, or any other binary regression model that you might dream of, so I'm sure all of you dream of those kinds of models, it's best to put the data, or I should say, it's best to not use a Bernoulli response format with your data, if at all possible. Instead, it's best to use a binomial response data format, even if the data didn't arise in a binomial way. And so what I always do is that once I've determined which variables to include in like a logistic regression model, I put the data in what's called explanatory variable pattern form, or EVP form for short. This is not necessarily a standard term that you see other people use. I don't think there's necessarily a standard term that people use for it. And basically what that means is transform your Bernoulli format data to a binomial format. So we've actually even kind of already did that before. If you remember back in chapter 2 with the place-kicking data set, we first estimated the model to the Bernoulli format. And then we say, hey, How about we just consider distance alone and transform the data to a binomial format? So if we did that, and this is just the code directly from chapter 2, the binomial format to the data set, if we just only had distance itself, looks like this. So for example, at 18 yards, we had 2 successes out of 3 trials. Well, with the Bernoulli format, we would have 3 rows to our data frame to represent that. Now we're just going to have 1. Also, at 21 yards, there were 19 successes out of 20 trials. So now again, it's a binomial format, or what I like to call explanatory variable pattern form. Because what we're doing, if you think of it in a larger context, let's say with all your variables, we're looking at all the unique explanatory variable combinations, and we're just simply summing up the number of successes and summing up the number of trials for each unique explanatory variable combination, or each explanatory variable pattern. That's what the binomial format essentially says. So for example, if I was looking at a situation where I had both distance and PAT, then I would have a variable here called PAT, and I would have a row that has 0. I would have another row that has 18 and 1 there. And I would separate out the number of trials where I had distance of 18, PAT 0. Number of trials with distance of 18, PAT 1. Look at the number of successes at each of those variable combinations. Is everyone clear on what explanatory variable pattern form is? Okay. Well, let's talk about a little bit right now, why do we want to do that? Because I'm sure that's what you're all wondering. Not when is it ever going to become 3:45? The reason being is because these tools that we're going to use are going to be like statistics that we're going to calculate for every single observation. And we're going to have to make a continuous distribution approximation to these statistics. The problem, though, is that these statistics are actually have a discrete distribution to it. And so because of that, then, by getting essentially a larger number of observations per, let's say, row of your data set with these statistics, we are more likely to have a better continuous distribution approximation. You'll see a better example of that coming up, but I thought it's good to at least give you a little bit of idea of why we're doing this. So the key then to get out of this is, well, what is EVP form right now? And also, whenever we consider a model from chapter 2, it's always going to be an EVP form. Now, before we get to the next little subsection here, let me ask you a question. Suppose you had one variable x, and it was truly continuous. How many, well, what would EVP form basically represent? X was truly continuous. Let's say you originally had Bernoulli observations. You want to transform it to EVP form. Who can wait the longest?
Probabilities.
Excuse me?
Probabilities.
What do you mean by probabilities?
You have
I'm just looking at a data format. I'm not really concerned about probabilities. Well, I'll give you a leading question. Will my data format change at all? Will my data change at all if I go from a Bernoulli format to an EVP format, if X was truly continuous?
no.
The answer is no, thank you. Why?
Because,
What?
uh, X is continuous, you wouldn't have 0 ones, you wouldn't have penalty with you. First place.
I don't think you quite get it. Let me put it in the context of the place kicking data set. Suppose distance, for some reason we were able to say distance was absolutely continuous. So, when you watch a football game, the announcer might say, he's going to attempt a 20.3456 yard field goal. Would you expect a field goal kicker ever to attempt exactly the same distance at any time during a football game? No. Okay, so if you convert the Bernoulli format to an explanatory variable pattern format, what's going to happen? You're going to have no change. It's going to be exactly the same. Because each distance essentially would be unique in the data set. So in that particular case, then converting to EVP format is not even really worthwhile. And so that is actually going to cause us a problem when we have continuous explanatory variables that are exactly continuous. You might be saying, well, let's say that I might have, we'll say, what would be a good variable? I can't think of one. You'll see eventually as we go along. So let's talk about residuals. Residuals are a great way to determine, well, is a particular observation predicted well or not? Simply what a residual is, and you should have seen this in like a Stat 801 course. It's in regular regression. Observed value minus the estimated value. So with respect to Chapter 2 models then, that means your observed y, which would be now a binomial response, the number of successes out of n trials. You take y minus n times pi hat, which would be how many successes would I expect given my model. That will be the residual. We want y to be close to n times pi hat. The closer it is, the better the model, essentially. With respect to Chapter 4 models, where y is a count, you would compare that to mu hat. Again, the closer y is to mu hat, the better the model. So for example, with respect to the place kicking data set, then at 21 yards, you might remember there were 19 successes out of 20 trials. So y was 19, n was 20, pi hat, if you actually went back to Chapter 2 and used that model, I actually showed the model there, I get 0.9676. So my residual is negative 0.3519. So essentially, the model is overestimating the number of successes by a little bit. I mean, of course, you can only have integer values for y anyway. So you're probably going to be a little bit off. But of course, what we want to know, though, is, well, is this being off by this much? Is this okay? Is this reasonable? Or is this saying, uh-oh, the model's not fitting this observation well? We'll make that determination later. So here are some notational changes so we can talk about Chapter 2 and Chapter 4 at the same time more easily. I will always use y hat to denote the estimated value from the model. So n times pi hat will be y hat for Chapter 2. Mu hat for Chapter 4 will be y hat. It's just going to make it easier for us to discuss. So now my residual will always be, no matter which model I'm talking about, Chapter 2 or Chapter 4, y minus y hat. Now overall, let's say that we have capital M observations. Then what I want to do is actually calculate these residuals for every single observation. So for the mth observation, I would have ym minus y hat of m. With that then, we can start making judgments about, well, how far does y hat need to be from y before I say, uh-oh, there's a problem with my model. And that's where we start getting into excuse me, things called Pearson residuals. This is what a Pearson residual is. We're going to call it E sub m. We're going to calculate for every single observation in my data set. So when I say observation, I'm talking about, let's say, with explanatory variable pattern form data, m different rows to my data set. That would be each row is an observation. We take our residual and we divide by the square root of the estimated variance of y sub m. So the reason why we do that is because we know that y is going to vary. And when we take that into account, that variance, we have a way to judge, is that residual big in absolute value or not, relative to the variability that we would have in y. But what is this variance? So let's say I have a logistic regression model. What would be the estimated variance of y? What's the distribution of y? Starts with a B. Binomial, thank you. So what's the variance? So that's my variance. That's what you would put in the denominator. How about for a pro-bit model? What's the variance of y? Or is it a trick question? It's the same. Trick question. Because it's y. I don't care what my link function is. Y still has the same distribution. How about for a Poisson? What's the estimated variance of y?
Yeah.
What?
Yeah.
Mu. Or how about we put in the context of our new notation, y hat sub m. So, let's calculate a Pearson residual here. For a distance of 21 yards, again, there were 20 trials, 19 successes. This was the fourth, essentially, observation in this explanatory variable pattern form of the data set, the fourth row. So if you go through all the calculations, you get negative 0.4449 as the Pearson residual. Well, what do we do with that? Well, think about what a standardized quantity is and what kind of distribution we use with a standardized quantity. This is essentially a standardized quantity. Take the statistic minus what I estimate that statistic to be, essentially, divide by square root of the variance. So I could use a standard normal distribution approximation with each of these Pearson residuals. And what do we know about the standard normal distribution? Well, it's symmetric. It's mound shaped, centered at 0, and if you get beyond maybe 2 or negative 2, hey, it's kind of unusual. You expect about 95% of your observations to fall within negative 2 and positive 2. So, what do you think about this Pearson residual here and for this observation? Do you think this observation is being reasonably fit by the model, or is there something going on, something unusual? Well, seems like things are okay. If I had a Pearson residual that was outside of plus or minus 2, I'm going to say, be careful with saying that, but I'm going to say it right now. If I had something outside of plus or minus 2, that would maybe throw up a little bit of an alarm bell to me that, hey, maybe something's going on wrong here, because it's unusual. I would expect using if this normal distribution works really, really well, I should have 95% of my residuals between Pearson residuals between negative 2 and positive 2. Now, what we will find out, though, shortly, and we won't be able to get to today, is that this normal distribution approximation can actually be quite poor, which makes making judgments about observations with respect to the residuals difficult when you're dealing with generalized linear models. It is 3:45. Are there any questions? Okay, that's it for today.